I now want to talk about sums of combinatorial games. What do we mean by making a sum of two games? Well, say we have games G1, G2 through G sub n. We have n different games. They could be the same, they could be different. Just in general, n combinatorial games. When we talk about a new game, G, which is the sum of the games G1, G2 through Gn, what we mean is the following. Think of the games as being played separately here. We have two players. We have player 1 and player 2. They alternate taking turns. Each one on his or her turn will do the following. First, choose a game. Player 1 could choose to start with game 2, for example. Make a legal move in game 2. Then player 2 gets to choose a game. Maybe it will also be game 2. Maybe it will be game 3. Maybe it will be game 7, if there are 7 games. And make a legal move in that game. And then they alternate, each one taking turns, picking a game and making a legal move in that game. The game ends when neither player can move anymore. There's no legal move in any of the games left. We're using normal play rules, so the last player who was able to make a legal move is the winner. That's what we mean by the sum of combinatorial games. And if we want to start to analyze combinatorial games, we're going to want to know things like what's the Sprague-Grundy function for this sum of games. Well, the only way we're going to be able to do that is, let's say we know the Sprague-Grundy function, call it little g sub I is the Sprague-Grundy function for the game capital G sub I. That's for each I equals 1 to n. So if you know the Sprague-Grundy functions for each individual game, the question is, how do you get the Sprague-Grundy function for this new sum of games where players alternate turns and get to pick, taking a move at any game they want? Player 1 picks a game, makes a move. Player 2 picks a game, makes a move. Player 1 goes back, picks a game, makes a move. What would the new Sprague-Grundy function be? And here's the amazing theorem called the Sprague-Grundy theorem. It says you can find the Sprague-Grundy function for this sum of games. We'll write that as just little g. Here I'm writing g of x1 through xn. x1 is the position in game 1. x2 is the position in game 2. All the way to xn is the position in game n. The Sprague-Grundy function for that position, x1 through xn, that n tuple is your position in the sum of games, is just exactly the nim sum of the Sprague-Grundy function for game 1 at position x1 plus the Sprague-Grundy function for game 2 at position x2, all the way up to the Sprague-Grundy function for game n at x sub n. So this is why the Sprague-Grundy function is useful, precisely because when you look at the sum of games, everything behaves nicely. The Sprague-Grundy function for the sum is the sum of the individual Sprague-Grundy functions. And since knowing the Sprague-Grundy function tells you how to have a winning strategy, I'll remind you how that works. P positions are when the Sprague-Grundy function is 0. N positions are when the Sprague-Grundy function is non-zero. If you know that know the Sprague-Grundy function for each individual game, in other words, that will tell you how to play each individual game, then you know how to play the sum of games. How? You just compute this nim sum of those individual Sprague-Grundy functions. If that's 0, you're in a P position for the sum of games. If it's non-zero, you're in an N position, and the winning move will be to find a game where you can make a move that will turn the Sprague-Grundy functions, the nim sum, I should say, of the Sprague-Grundy functions to 0. Now, how do we prove the Sprague-Grundy theorem? To prove the Sprague-Grundy theorem, we have to show that the Sprague-Grundy function for this sum of games really behaves exactly the way we want it to. In other words, the Sprague-Grundy function, I'll rewrite it up here because it was on the previous slide. We want to show the Sprague-Grundy function for the sum of games at position x1, x2 through xn. That means game 1 is in position x1, game 2 in position x2, up to game n in position xn. We want to show that that's just equal to g1 of x1, nim sum with g2 of x2, nim sum up to g sub n of xn. And what does it mean to say this is the Sprague-Grundy function for g at this position? Well, it means the minimum excluded number for all followers of this position is exactly this nim sum. Well, we're just going to give the name b here to this nim sum on the right. And I'm going to show b is the minimum excluded number among all followers of g of x1, x2 up to xn. What does that mean, to say it's the minimum excluded number among all the followers? Well, for every non-negative integer a which is less than b, there must be a follower that has value a. That's what we have to. That's one of the things we have to show, because if there were any a where we didn't have such a follower, then you would have a smaller minimum excluded number. It wouldn't be b; it would be a or something smaller than a, because a wouldn't be excluded. So we need to know, to show that b is the correct value for the Sprague-Grundy function, that a follower of this position can get you any number 0, 1, 2, 3, all the way up to b minus 1. That's any a less than b. And then, to show b is really the minimum one, we have to show that no follower has g value of b, that you don't have a follower that actually hits b, so b really is an excluded value among all the followers. And then we remind you what we mean by a follower. A follower of this position is a new position that you get to in this sum of games when you pick one of the games. If it's x1, for example, a follower means you pick x1, you go to a follower. In our book, we call it x1 prime, for example. You change your position in game 1 from x1 to one of its followers, and you leave all the others the same. You might pick game 2, in which case you would change x2 to some x2 prime using a follower of x2. A follower of this position, which is an n-tuple, is another n-tuple where only one of the positions is changed, and the one that's changed is changed from some position in the game to a follower in that same game. So we have to show these two things. Every non-negative integer a, for every non-negative integer a less than b, there's a follower that has Sprague-Grundy value a. Well, to show property 1, we're really going to just extend our method for finding a winning move in nim, and we'll extend it in the following way. We're going to first define a new variable, a new number d, to be a plus b, the nim sum of a and b. So a is the kind of desired target where we want to find the follower of the position with Sprague-Grundy value a. We'll take a, we'll look at the nim sum with b, and then essentially we're going to do what we did when we asked the question in the nim strategy: which pile do I have to take stones from? We look at that nim sum here and we ask, where's the biggest one? So here, the way we do that formally is we say, let k be the number of digits in the binary expansion of d, so that the number of d, this should be 2 to the k minus 1, not 2k minus 1. That was typed in wrong. And this should be 2 to the k. So this number d is between 2 to the k minus 1 and 2 to the k, possibly equal to 2 to the k minus 1. So we look where that leading one in the nim sum of a and b is. That's that farthest position going from right to left, the farthest position to the left, where there's a 1 in that binary expansion here for d. So there's a 1 in the kth position. Since a is less than b, A is a smaller number than B, B will have to have a 1 in that kth position, and A will have to have a 0 there. Why is that true? Well, if A also had a 1 there, in the nim sum, those would cancel out. So that's impossible. And if B didn't have a 1 there, then the nim sum of A and B would have a 0 there, and we chose that position, that kth position from the right, to be one where the nim sum is equal to 1. That means 1 has a 1 and 1 has a 0. The one with the 1 has to be B, because A is less than B here. Now, since B was by definition this nim sum of g1 of x1 plus g2 of x2 all the way up to gn of xn, there has to be some one of the x sub i's such that the binary expansion of g sub I of x sub I has a 1 in the kth position. Why does one of these have to have a 1 in the kth position? It's because B has a 1 in that kth position, and if all of these had only zeros in that kth position, that would be impossible. So here, just for simplicity in writing things down, let's assume that it's in position 1. All the arguments would be the same if we did everything in position 2 or position 3 or any other fixed position. So if we assume that there's a 1 in that kth position in g1 of x1, then if we take the nim sum of D with g1 of x1, I claim that's going to be less than g1 of x1. Why? Because the 1, which is the lead 1 in the binary expansion of D, will cancel out with the 1 in the dth position of g1 of x1, because they both have 1s in that same position, and the way the nim sum works is that will turn that to a 0 in that position. So that number will be smaller than g1 of x1 was to begin with. And what does that mean? Well, g1 of x1 is some number such that well, since g1 is the Sprague-Grundy function for game 1, at position x1, that's the minimum excluded value among all followers of x1. So since this number is a smaller number, there's a legal move from x1 to a new position, x1 prime, where you get exactly this as the new Sprague-Grundy value. You get anything smaller as a Sprague-Grundy value among some follower. So we're going to define x1 prime to be a new position, a follower of x1, where this is true. Then what happens? Well, when we look at this new nim sum with x1 prime instead of x1, g1 of x1 prime is exactly d nim sum g1 of x1. All the rest are the same. And that's the same as d nim sum with this stuff, which is all b. And d nim sum with b is, by definition here, well, not by definition, it's by this here. Remember here, d was equal to, by definition, a nim sum b. So d plus b is a plus b, which is exactly a. And what does that tell us? That's actually what we wanted to show, that for any non-negative integer a, which is smaller than b, there's a follower which has g value. That's the Sprague-Grundy value for this function g that we propose. Well, it's the value of g, which is our proposed Sprague-Grundy function, which is exactly equal to a. That might seem a bit abstract, but this is exactly what we were doing when we were solving nim. We looked at the nim sum of the entries. We asked, where's the biggest one in the nim sum? And then we make a move from one of the piles, which had a 1 in that same position. And there we just chose a following position that turned that 1 into a 0. This is really the same thing, only we're turning the Sprague-Grundy value into some arbitrary thing that we want, the number a, by letting d be a nim sum b, and just making the algebra work out. To show part 2, what was part 2? That part 2 said that when you make any legal move, you have to lessen the value of this new function g. You can't keep the same value of g. Suppose to the contrary that starting from our position, this n tuple x1 through xn, there were a follower with the same g value. we're going to show that that's impossible. So we're going to suppose it's true, and suppose without loss of generality that the move to the follower is in the first position. Everything would be the same if we're in any other position. So what does that mean? That means we're supposing that there's a follower x1 prime of x1, a way to move in the game 1, such that g1 of x1 prime, nim sum with the other g's, is the same as g1 of x1, nim sum with the other g's. But then we can use the cancellation law. What is the cancellation law? The cancellation law says that if a plus b is equal to, let me call it c plus b, then a equals c. We just cancel the b's. Does that work with nim sums? Yes, it does. Why? Well, if a plus b equals c plus b, then a plus b, when I just add b again, I get c plus b again with all nim sums. And b plus b is 0 here, and b plus b is 0 here, and taking the nim sum with 0 doesn't change things, so that implies a equals c. So we're allowed to cancel things. Here we cancel everything here, and then we get g1 of x1 prime must be the same as g1 of x1, but that's a contradiction, since in game 1 you can't have a follower of position 1 with the same Sprague-Grundy function. By definition, g1 of x1 is the minimum excluded value among all followers of x1. It can't be the same as the Sprague-Grundy value at a follower of x1. So what have we shown? We've shown, going back here, that these two conditions are really both true, and that tells us that, going up one more page here, the Sprague-Grundy function for the sum of games really is the nim sum of the individual Sprague-Grundy values. We'll be talking about examples of sums of games more in our Zoom meetings when we'll try to play some. But the simplest example is just nim. I claim nim, when you have n piles, is just a sum of games where you have n individual one-pile nim games. So let's say you have 3 stones in one pile, 4 stones in another, and 5 stones in another. If we consider this just a one-pile nim game, game 1, this would be game 2, this would be game 3. One-pile nim is, of course, a very simple game, and we already know the Sprague-Grundy function for one-pile nim g of n is precisely n. When you have n stones, the Sprague-Grundy value is exactly n for that position with n stones. So the Sprague-Grundy function for the 3-pile nim, or let me say, let's start again. 3-pile nim is just a sum of games because it's like 2 players, they alternate terms, picking one of the games, one of the one-pile nim games, and making a legal move. Then the other player picks one of the one-pile games and makes a legal move. That's how nim works when you have multiple piles. So what does the Sprague-Grundy theorem say? It says the Sprague-Grundy value for position x1, x2, x3 is just g1 of x1 plus g2 of x2 plus g3 of x3, where these are nim sums. And of course, g1 of x1, g1 is just the Sprague-Grundy function for game 1, g2 for game 2, g3 for game 3. g1 of x1 is just x1. For x2, it's just g2 of x2 is just x2. And for x3, we just have x3. g3 of x3 is just x3. So the Sprague-Grundy function for a general nim position with x1 in the first pile, x2 in the second pile, x3 in the third pile is exactly this nim sum, x1 plus x2 plus x3. So how do you win at nim? Well, you win, P position is when the Sprague-Grundy function gives you a 0, that's when the nim sum is 0, and an end position is when the Sprague-Grundy function is non-zero, that's when the nim sum is non-zero. That's exactly what we had shown previously.